All right, so the last important subsection under the special continuous probability distribution that we want to consider is the normal distribution. So the normal distribution is one of the most widely used probability distribution for modeling random experiments. The normal distribution provides a good model for continuous random variables involving measurements such as time, height or weight of persons, marks scored in an examination, growth rate, and many other scientific measurements. Okay, so the normal distribution was introduced by the French mathematician Abraham de Moivre in 1733. He actually developed the mathematical equation of the normal curve and also used it to approximate probabilities associated with binomial random variable when the sample size is large. And this is related to the central limit theorem, which provided a basis from which much of the theory of inductive statistics is founded. Okay. However, in 1809, Carl Friedrich Gauss used the normal distribution to solve important statistical problem of combining observations. Okay. That is, he was able to derive the normal equation from a study of errors in repeated measurement of the same quantity. Because Gauss plays such a prominent role in determining the usefulness of the normal distribution is often called the Gaussian distribution. Okay. All right. So let's take a look at the definition for normal distribution. And the continuous random variable x is said to have the normal distribution with parameters mu and sigma squared if its PDF is defined as shown in equation 2.31. Okay. All right, so let's take a look at some properties of the normal distribution. The normal distribution curve is bell-shaped. Also, the mean, median, and mode are equal and are located at the center of the distribution. The curve is symmetric about the mean, that is, its shape is the same on both sides of the distribution when divided at the middle value. The total area under the normal curve is 1, which implies that the area to the right of the mean is 0.5 and the area to the left of the mean is also 0.5 or 50%. Okay. Now it is also asymptotic to the x-axis, that is, the curve gets closer and closer to the x-axis but never touches it. Okay. All right. So in order to understand these properties, let's take a look at the following graphs. So this figure is showing us the normal curves with different means but equal variation. Okay. So you can see the bell-shaped curve here. So this is how the bell curve shape looks like. And you can see that here we have the mean to be at the center, but in practice, the mean, median, and mode are all located at the center. So the area to the left of the mean is 0.5 or 50%, and the area to the right of the mean is also 0.5 or 50%. Okay. And you can see that the curve seems to get closer to the x-axis, but it will never touch it. Okay. So this shows the asymptotic property. All right. We also have normal curves with equal means but different variations. We can see for the first distribution, the curve seems to be high and thin, but for the second distribution, the normal curve seems to be flat and spread out. Okay. And we can also have normal curves with different means as well as different variation. Okay. All right. So let's take a look at the mean, variance, and moment generating function of the normal distribution. So the mean is equal to mu. We have the variance to be equal to sigma squared, and we have the moment generating function also as shown here. Okay. All right, so let's take a look at the standard normal distribution. So what is the standard normal distribution? The standard normal distribution is the distribution of a normal random variable with a mean of 0 and a standard deviation of 1. Okay. So the standard normal random variable is often denoted by z and often referred to as the z-score. Mathematically, the standard normal distribution is expressed as shown in equation 2.32. So this equation basically means that we are looking at the number of standard deviation that a particular value of the random variable will be away from its mean value. Okay. So the main reason behind standardization or the standard normal distribution is to ensure that random variables with different units of measurement are put on the same scale for easy comparison. Okay. The reason being that each normally distributed variable has its own mean and standard deviation, which makes their curves to have different shapes and locations. Okay, so this means that in practical application, one will have to get a table of areas under the curve for each variable, and this will become very tedious to do. So in order to ensure that random variables with different units of measurement are put on the same scale for easy comparison, we employ this technique of standardization. Okay. where anytime you standardize a variable, it will have a mean of 0 and a standard deviation of 1. And it will always range between these two values, minus 3.49 and 3.49. Okay. So this how the standard normal curve will look like. Okay. So the mean will be 0 and the variations, the incremental variation is just 1. Okay. So based on the standard normal curve, there is a rule of thumb known as the empirical rule, which is often used as a descriptive tool only when the data tend to be roughly bell-shaped. Okay, so thus the empirical rule states that given any distribution that is bell-shaped in this form, okay, approximately 68% of the observation will lie within one standard deviation of the mean, and approximately 95% of the observation will fall within two standard deviation of the mean, and approximately 99.7%, okay, of the observations will fall within three standard deviation of the mean. Okay. All right, so let's take a look at finding areas. How do we find areas under the standard normal distribution? So the area under the standard normal distribution curve can be obtained using the standard normal table. Okay, so I have my Z table here. This is the standard normal table. So I'll try and leave this in the description of this video so that you can download it. Okay, or you can even download one online. So we have the first part, that's the negative part, and we also have the positive part. Okay. All right, so let's go back to our slide. Now the area under the standard normal table is cumulative. Okay, so finding areas to the left of Z or to the right of Z can be traced from the table where the first decade that is looking at the first column in the table and the last decade that is looking at the first row in the table intersect. Okay, so for instance, if I want to look at 1.22 or let's say 0.52, I'll first of all check the first two decades at the first column. Okay, so here 0.5 and the last decade, which is 2, can be traced at the first row of your table. So 0.2 is here and 0.5 is here. So where they intersect, you can pick the corresponding area. Okay, we'll take an example and learn how to read from the standard normal table. Okay, now let's go back to our slide. Finding areas to the right of Z can be obtained by using this complementary rule. So because we know that once you add the area to the left and the area to the right, it must add up to 1. And because it is cumulative, if you want to find the area to the right, you have to use this complementary rule, 1 minus probability that Z is less than a particular value of Z. Okay, and this cumulative, right, can also be obtained using this phi notation. Okay. Now, finding areas between Z can also be obtained using this approach. Okay, you just have to subtract the lower limit from the upper limit, okay, which can also be represented in this form. All right, so let's take an example. If Z follows a standard normal distribution, we want to find a probability that Z is less than or equal to 1.76, and secondly, probability that Z is greater than 1.76, and also Z is less than minus 2.02, and lastly, that's not the least, want to find a probability that Z is between minus 0.75 and 1.32. Okay, so let's take a look at the solution. So from the standard normal table, the area to the left of Z, which is equal to 1.76, is 0.9608. Okay, and this is how the curve will look like. So the mean will be 0. So we have it at the right side. So this is Z score 1.76, and the area to its left is the area to its left is 0.9608. Okay, so how do we read this from our Z table? So first of all, we are going to locate the first two decades at the first column. So 1.7 is here. Let me try and draw this. So we have 1.7 here. Okay, we have some. Check it to the 6. So the last decade, which is 0.06, can be obtained on the first row. So where they intersect, you pick the corresponding area. So this is going to be area. Okay. Let me try and use it. So if you check the results, we had 0.9608. Okay. All right. Let's take a look at the second question. So from the standard normal table, the area to the right of 1.76 is obtained by subtracting the area to the left of z, which is equal to 1.76 from 1. Okay, so that is, we can obtain this by using this complementary rule. So we already know this to be 0.9608. Okay, so once you do the subtraction, you obtain this result, and this is how the curve will look like. Okay, all right, and let's take a look at the third part. From the standard normal table, the area to the left of z, which is equal to minus 2.02, is 0.0217. Okay, and this is how the curve will look like. So this time our z is negative and the area to its left is 0.0217. So how do we read this from our table? Let's check that. So now our z is negative, the z score is negative, so I'm moving to the negative side. So let me try and draw this. So we are looking for minus 2.02. So the first two digits can be traced there. Okay, so and we are looking for the last digit is 0.02. So this is where they intersect. So this is the corresponding area, 0.0217. Okay, so we can see that from our solution we had the same result, 0.0217. Okay, all right, now let's take a look at the last part. From the standard normal table, the area between minus 0.75 and 1.32 is going to be 0.6800. Okay, so how do we obtain this? So this can be expressed in this form. Okay, so we subtract the lower value from the upper value. Okay, so this is the cumulative of the upper value and this is the cumulative of the lower value. And once you read this from the table, you obtain this. And once you read this also from the table, you obtain this. Okay, I guess by now you can read this. Let me guide you once more. So let's take a look at 1.32. Let's go back to our z table. So 1.32. All right, so I have 1. Let me try and draw this. So we have 1.3 here. Okay, we are looking for 2. Okay, so this 2, sorry, this 2. Okay, so this is where they intersect, 0.9066. Okay, the second part is minus 0.75. Okay, so let's take a look at that. And that will be at the negative side. Minus 0.75, minus 0.75. Okay, all right, so let me try and draw this. So we have minus 0.7 here, and I'm going to trace it to 0.5. Okay, so I think this 0.5. Okay, so once you trace it, the intersect here, so this is the corresponding area, 0.2266. Okay, all right, so trace it. All right, so let's go back to our slide. So you can see that once you do the subtraction, you obtain that. Okay, this is how the area will look like under the curve. Okay, all right, so now let's take another example, finding z-scores and some constant. Okay, so the z-score can be in the form of z index 0. Sometimes you can also use k for z-score. Okay, so I want to find these constants. How do we obtain them? Let's take a look at the first part. So we want to find the probability that z is greater than a particular value of z-score, and the area is given us to be 0.1234. Okay, so how do we obtain this z-score? So we can express this in this form. Okay, and this can also be expressed in this form. So once we make this a subject, we obtain this. So we're going to take this to this side and this one to the other side. Okay, so once you do the subtraction, you obtain this. Now to get this z score, we try to take the inverse. Okay, so this is the inverse of the standard normal. And how do we get the corresponding z value? So basically, we are looking at the corresponding z value that has an area of 0.8766. Okay, so how do we obtain this z score? So let's jump into our z table. So we are looking for 0.8766. So it will be at this side, 0.878766. So let me draw this. So we can see that it is somewhere here. Sorry for the sketch. It's between these two values, okay? It's between these two. So the 0.876 is between these two values. So we'll take the corresponding z-score 1 point, we'll take the average of these two 1.15 and 1.16, okay? So let me try and erase this. So let's go back to our slide now. So once you take the average, you get a corresponding z-score, okay? All right, so let's take a look at the second part. Want to find the z-score to the right side, okay? So, we can express this in this form, and this is similar to that. So once you read this from your standard normal table, you obtain this. If the data subject, you obtain that. So once you add this to, you obtain this. So now to get our z-score, take the inverse, and we know how to do this, okay? So let's try and read this again. So let's go back to our z table. So 0. Let me check it again. 0.8. We are looking for the corresponding z-score that has this area, 0.9822. So let me check. 0.982298989822. Okay. So we have 9822. I think it will be somewhere here. 9822. So I think it will be between these two. Yeah. Okay. Or let's say 9822. Yeah. It will be between this 9822. I think it will be between this approximately equal to that. So let's try and take 2.1, 2.10 and 2.1. Okay. So it will be between these two. So let's see. So 2.10 and 2.11. Once you take the average of it, you get this. Okay. Very quite simple. So let's take a look at the third part. So I want to find another z-score to the left. Okay. We have it on the left side of the mean. So let's take a look at this. We can express this in this form, right? And this can also be expressed in this form, okay? And we can read this from our normal table to obtain this. So once we make the subject, we obtain that. And once we make k the subject, okay, we can take the inverse of it. So once we do the subtraction, obtain this. So we are looking for the corresponding score that has an area of 0.266, and you already know how to do this. So once you read from the table, you obtain this, okay? All right, so the last part, we want to find two unknown values, okay? So how do you obtain this? Two unknown z values. So this can be expressed in this form. It can also be expressed in this form, okay? We can basically express this side in this form, okay? Because once you add these two, it must be equal to 1, okay? So once you work this one out, you obtain this. And once you make this a subject, okay, you obtain that. So we are looking for k, so we can take the inverse of it. Once you divide this, you obtain this. So the corresponding z value that has an error of 0.88 will be between some two values. So once you take the average of it, you obtain that. And I hope you can read this from the standard table, okay? All right. So let's try and take another example. Let's see index alpha be defined by this equation, where z is following standard normal distribution. So I want to find z index 0.05 and also z index 0.975. Okay, so how do we do this? So this can be expressed in this form. This is basically similar to the example we just saw. So we are trying to look for the z-score that has an area of 0.05. Okay, but sometimes you can have it expressed in a different form. So this is another way to get a z-score having an area of 0.05. Okay, so once you reach from your standard normal table, you obtain this. Let's try and get this. So we are looking for a z-score that has an area of 0.05. So let's try and check this. So 0.05 will be somewhere here. 0.05, 0.05. I think it's between these two values. Okay, let me try and draw this. So we have this. 0.05. Okay, so between this and this, 0.05 is between these two, so we take 1 point minus 1.64 and minus 1.65, take the average of these two to get that corresponding value. Okay, so let me try and erase these two. All right, so let's go back to our slide now. So once you take the average of these two, you obtain this result. Okay, this should be equal to minus 1.615. All right, so the second part, we are looking for the corresponding z value that has an error of 0.975. So if you use similar approach, you're going to obtain this result, 1.96. Okay, quite easy to do. All right, so now another example. Each week, a certain household generates on average 28 pounds of pure water sachet for garbage, assuming that the standard deviation is 2 pounds and that the variable is approximately normally distributed. If a household is selected at random, want to find the probability of it generating between 27 and 31 pounds per week, and also generating more than 30.2 pounds per week. Okay, so let's take a look at the solution for this. So let x, for the first part, let x denote the random variable in pounds of household will generate pure water sachet for garbage per week. Okay. All right. So we want to find the probability that the household will generate between 27 and 31 pounds of garbage. Okay. And this can be expressed in this form using the cumulative approach. Okay. So basically, we are going to transform this using the standard normal distribution. So this can be using the z-score, we have to subtract the particular value from the mean and divide by the standard deviation. Okay, we do the same for the lower limit of the value. Okay, so once you work this one out, you obtain this result. And we know this is similar to that. So once you read this from the standard normal table, you obtain this. If you reduce, you also obtain that. So once you do the subtraction, you obtain this. Okay. So this basically means that there's approximately 62% chance for a randomly selected household to generate between 27 and 31 pounds of pure water sachet for garbage per week. Okay. All right. So let's take a look at the second part. I want to find the probability of a particular household generating more than 30.2 pounds per week. Okay. So this can also be expressed in this form, and using the standard normal distribution, we can have it in this form. It can also be expressed in this form. So once you read this from your table, you obtain that. So once you do the subtraction, you obtain the result. Okay, very quite simple to do. All right. So now finding data values given specific areas. How do we find data values when we have some specific areas? A normal distribution can be used to find specific data values for given areas. So given that we have the z-score as shown in equation 2.33, it can be deduced from equation 2.33 that the continuous random variable x is obtained by using equation 2.34. Okay, so if you make x the subject from equation 2.33, you obtain this result as shown in equation 2.34. Okay, where z is equal to z index alpha for a given area alpha. Okay, we already know this. Okay, so let's take an example. For a medical study, a researcher wishes to select people in the middle 60% of the population based on blood pressure. Okay, if the mean systolic blood pressure is 120 and the standard deviation is 8, want to find the upper and lower readings that would qualify people to participate in the study. So let's take a look at the solution. So let X denote the possible measurement of systolic blood pressure such that X1 and X2 are the lower and upper readings respectively. Okay, so we can have our curve in this form where this 0.60 is showing as the middle 60% of the blood pressure. So to the, we know the mean is 120. So to the left of the mean, we have 30%. And to the right of the mean, we also have 30%. Okay. So we can basically transform this using the standard normal. Okay. So this is the standard normal. So we want to find a correct. Once we're able to get this z scores, z1 and z2, we can basically find the given data value that is x1 and x2. Okay. So basically, we know that the area between 0 and z1 is 30%. That's the expression that we have here. And this can be expressed in this form, okay? So once you make this a subject, you obtain this. Once you read this from the table, you obtain that. So once you do the subtraction, you obtain this. And you have to find z1, take the inverse. So the inverse, you know how to read from the inverse of the standard normal. So this is equal to that, okay? All right, so we also know that the area between 0 and z2 is 30%, which can also be expressed in this form. Okay, so once you make this a subject, you obtain that. You can read this from our table to obtain this. So we make z2 the subject, you obtain that. And once you read from your table, you know how to read this, you obtain 0.84, okay? All right, so now we want to find x1, which can be obtained using the formula or the equation by using the formula in equation 2.34, okay? So once we input our values, we obtain this, which is equal to that. And x2 can also be obtained using this same approach. So once you input your values, you obtain this, which is also equal to that, okay? So basically, this means that for people to qualify to participate in the study, their systolic blood pressure must range between 130.28 and 126.72, okay? All right. So before we bring this tutorial to an end, let's take a look at some theorem, the normal approximation to the binomial distribution. If x is a binomial random variable with mean, mu which is equal to np, and variance which is equal to npq, then the limiting form of the distribution, which is shown in equation 2.3, will follow a standard normal distribution as the sample size becomes large. Okay, this theorem basically saying that if you have a binomial random variable and the sample size is very large, then you can basically approximate it using the standard normal distribution, okay? That's basically what it means, okay? So in that theorem, we have the normal approximation to the Poisson distribution. So let x be a Poisson random variable with mean lambda. So then for large values of lambda, as the Poisson random variable, the mean of it is becoming very large, we can also approximate it using the standard normal distribution as shown in equation 2.36, okay? All right, so this is going to be a trial question. I'll leave the solution in the description of this video so you can check it out. Please, if you find value in today's tutorial video, don't forget to subscribe if you have not. And thank you for watching.